In our last video, we know the major effect of zero is to increase the overshoot. This figure shows the overshoot as a function of alpha, and alpha controls the locations of the zeros. When alpha is large, the zero is far away from the imaginary axis. It will have little effect on the response. Let's see in this case, when alpha is greater than 3, it has little effect on the overshoot. But when alpha is small, it is close to the imaginary axis. So it has an increasing effect as alpha is below 3, especially when alpha is 1 or less. So far, we only discussed the case when alpha is greater than 0. That means the 0 is at the left half of the S-plane. And the major effect of the 0 is to increase the overshoot. We know the total response, it contains 2 parts. So Y0T, let's call it original response. It is the step response for standard second order systems without zeros. Then the YDT is a time derivative of the original step response. Then we see its value is positive until the peak time of the original response. Then it has a large hump in the early part of the curve. By adding this to the original response, it lifts the original response and add it together to produce the overshoot. It's interesting to see the case when alpha is less than 0. So when alpha is less than 0, instead of adding the second part, so we subtract the second part from the original response. So when alpha is less than 0, we have 0 at the right half of the S-plane. So we call 0 right half plane 0 or non-minimum phase 0. So with here, the original response is the same, even though it looks different because of the y-axis. They do not have the same scale, but the original response is the same. Then instead of adding, here we subtracting. So the positive becomes negative, and the negative becomes positive. So when we subtract the original response by the time derivative of the original response, then we have the total response as shown here. So it's very interesting to see that even though the input is a positive signal, but the response will go an opposite direction from the input at the initial stage before it follows the input signal. So we call this undershoot. So here is overshoot, here is undershoot. So when the 0 is at the right half of the S-plane, it will first has undershoot before the overshoot. Now let's use an example to illustrate the complex zeros, the effect of complex zeros on the transient response. Let's consider the third order system with a pair of lightly damped poles. We have a pair of complex zeros, that is minus alpha plus minus beta j then we have one pole at -1, a pair of complex poles at -0.1 plus and -1. Now we want to determine the effect of the complex zero on the unit step response of the system for 3 different locations. So the imaginary part is always 1. We only change the real part. by using 0.1, 0.25, and 0.5. Here it shows the step response for 3 different locations. So when the zeros, the real part of 0 at minus 0.5 or 0.25, we clearly see the lightly damped oscillation. When the poles are close to the zeros, when the zeros are close to the poles, then the effect is reduced. The oscillation effect of the poles are reduced. Then when we move the zeros exactly at the locations of the poles, then we see the oscillation are completely eliminated in the step response. This is because of the zero pole cancellation. So the response, the step response will be the step response of a first order system. But in reality, usually we do not know the exact locations of the poles. So, but we can always move the zeros close to the poles to reduce the oscillation.